Uh, Hi, this is week 8, although officially the week 8 was the midterm, but we postponed the midterm to 2 weeks later. So we're going to resume week 9 instead, and after week 10, we'll be on the track. Okay. By the way, so we're not in our class. We're not going to have a midterm on the week 10. So we're going to wait a little bit more, so that the situation gets mild. Okay, so from this week, we're going to switch gears. So far we talked about the solution of differential equations, of single differential equations. From now on, we are going to talk about not only solving single differential equation, but also we're going to talk about solving several solutions, so finding solutions simultaneously of multiple differential equations. So for example, in the week 1, we talked about the epidemic model, and for example, in SIR model, they had it consists of 3 differential equations, and it consists of 3 functions, S, I, and R. So that's one of the examples of system of differential equation that we are going to talk about from now on. So in order to talk about that, we will talk about the matrices and some properties of matrices. So if you reading the book, then it's chapter 4. Chapter 3, we're going to skip chapter 3 for now. So we done until chapter 2. Now we're going to doing chapter 4. Okay. So the definition again, because some of you know the matrices, but some don't. So let me rephrase it again. So n by m matrix is a collection of m times m numbers, or it could be a function. So I will call it as an entries. And it's arranged by m rows and m columns. Okay, so they contains n times m entries. If one of the entry is missing, we don't call it a matrix. Okay. And usually when we say A, large A is a matrix, then we denote its entry as small a sub ij, where I appears as the first index, is the index of the row, and j, which appears as the second index, is the index of the column. So for example, if I say small a sub 2, 1 for here, right here, then it means that I'm calling entry on the second row and first column. So by specifying the indices of row and column, I can determine unique entry of the matrix. So if you have the same size of matrices, then you can add 2 matrices elementary wise. And also, regardless of the size of matrix, you can always multiply the constant. So k is here is a constant, for example, in this case, the real number. So when you multiply a constant to a matrix, the k times a is a new matrix whose elements are obtained from the original matrix A by multiplying k everywhere. Okay, not just one column or one row. You have to multiply your constant k to every entries of the matrix. And more important thing is that you can multiply 2 matrices only when you have this property. So if you want to multiply A and B in the order A times B, then it's possible only when your matrix A contains the same number of column with the same number of row of the matrix B. So you see the A is the first matrix in the multiplication and B is the second. And A contains the M column and B contains M row. That's only when you can define your multiplication. So in the result, A times B is another matrix, which is N by L matrix. So you see, when you multiply this N times M and M times L, this M cancels out. What you get is L times N times L. So that's the resulting matrix after multiplication. And how you define the entries of this A times B matrix? It's very easy because if you want to know what's the ith row and jth column entry of A times B, you have to take the ith row of A and jth column of B. Okay, and then you see, because we match this M together, there is a one-to-one correspondence between this row and this column because it has the same length. So you can multiply AI1 and BIJ together, and then AI2 and B2J together, and AIM and BMJ together, and then add them together. So this is ith row, jth column of A times B. Let me give an example. So let's say we have A as 2 by 3 matrix, 2 minus 1, 0, 1, minus 1, and B is 2 by 2 matrix, 1, 2, 0, minus 1. Okay. Now, can I take A times B? No, because the A, size of A is 2 times 3 and size of B is 2 times 2. These are not the same size. The size and the length of column of A is not equal to the length of row of the B. So this is not defined. You cannot define this multiplication. However, you can define B times A because B is 2 by 2 and A is 2 by 3. So you have same number of column and row. So these are equal. So when you cancel out these two, you will get the 2 by 3 matrix. Okay, so let's compute this. So B is 1, 2, 0, minus 1, and A is minus 1, 0, 1, 0, minus 1. So before I do the computation, I already know that this will be 2 by 3 matrix. So there will be 6 entries in this arrangement. So let's try to find 1 and let's try to find 6 here. Okay. So how do I find the entry in the number 1 place? So this number 1 is located at first row and first column of this matrix. So I have to take first row of the first matrix in the multiplication, which is 1, 2, right? 1, 2, and take the first column of the second matrix in the multiplication, which is 2, 1. You always have to read from the left and read from the top. So 2, 1. And then multiply pairwise and add them together. You get 4. So this entry is 4. Okay. How about 6? So 6 is located at second row and third column. So you take the second row from the first multiplication of the matrix, which is 0 minus 1, and then take the third column of the second matrix, which is 0 minus 1. So there's 1. Okay, so this is 1. So you can do the rest of the computation easily. So that's how we define the matrix multiplication. Okay. This camera just freeze. So let me. Normal. Okay. Yeah, I think that's okay. All right. So these are propositions. So first of all, if you have 3 matrices, you can multiply 3 matrices in any order. You can concatenate your multiplication in any order. So if you multiply A times B times C, there are 2 ways to do this multiplication. First, you take the multiplication of A, B, and then C, or you take multiplication of B, C, and then A. So the order of this concatenation doesn't matter. However, remember that the matrix multiplication is not commutative. You cannot change the order of the matrices. You can change the order of concatenation, but you cannot change the order of multiplication itself. Okay. And then the second one is that you can distribute the multiplication inside of this addition. And when I talk about this multiplication of addition, I'm talking about with the assumption that this multiplication is possible. Okay, so when I take A, B, C multiplication, then I'm saying that the size of matrix A and size of matrix B and size of matrix C all are defined so that this multiplication is definable. And also the similar distribution law holds. And if you have a constant K, then you can move freely inside of K. So this is only when you can change the order of matrix. So if you have a constant, then you can change the order, but not the matrix. So this is an important notion that the transpose of a matrix is that you just invert and you just change the row to column and column to row. So just invert your matrix. The row becomes column and column becomes row. So when you have a matrix entry Aij, then A of transpose of A becomes the entry is Aj. So which means that the i's, row, j's, column, entry of the transpose of A is Aij, which is so Aji, Aji, which is j's, row, i's, column of A. Okay, just change it. And the proposition about the transpose is that you take the transpose of transpose, you get original matrix. That's obvious. And you can take the multiplication of transpose of matrix, but that's equal to the transpose of the multiplication of K on the original matrix. And also transpose can be distributed along this sum, and this one is important. If you have a multiplication of 2 matrices, when it's possible, you can take the transpose of entire multiplication. However, this is equal to, you can distribute your transpose, but the order is reversed. So if you take the transpose of AB, then it's equal to transpose of B times B transpose of A. So not A times B, okay? So that's important property. And all things will be learned in the second grade when you learn the linear algebra. So one of the important things is the determinant. I think we already saw the definition determinant when we talked about the Wronskian. And in 2 by 2 matrix, and it's simple, we just take this part is positive and this part is negative. Okay, so this is positive and this is negative. For the 3 by 3 matrix, you have to remember this formula. That this is one of the formula to remember. This is original matrix, your A, and you take first two column of the matrix right here, copy to the right hand side here, okay, and then this direction you take positive sign, and this direction you take negative sign, and then add them together. Okay. So that's the one way. And also you can remember this formula using just 3 by 3 matrix. So if you take this multiplication, there are 3 ways of taking 3 multiplication of 3 entries on a different column and different row. So if I take the multiple of B11, B2 to B33, then these 3 entries are not in the same column or nor the same row. So there are 3 ways of taking such 3 entries. So this is positive, and this direction is positive, and then this direction, there are also 3 other ways, and it's negative. Okay. Okay. So and also when you have n by n matrix, which means that the number of row and number of columns are equal, we call it square matrix. You can define the inverse of matrix. Okay, if you have a matrix B such that A times B or B times A is identity matrix, this is just a matrix of special form where there are only ones on the diagonal and all the entries off diagonals are 0. So this is called the identity matrix. And if you have such matrix B, then this B is called the inverse of A and denoted by A to the negative 1. Okay. And when does this matrix A has an inverse? It's if and only if the determinant of A is non-zero. So if you have inverse matrix, it's called a non-singular matrix. If it doesn't have an inverse, then it's called a singular. So the theorem says that if the condition, the equivalent condition that the matrix does not have an inverse is when the determinant of the matrix is 0. In other words, if you take the same statement otherwise, the matrix A has an inverse if and only if the determinant of A is not 0. Okay, it's the same thing as this theorem. So that will be also be important in later. For now, let's move on to the inverse theorem, inverse matrix further. So we know how to find out whether this matrix has an inverse or not by simply calculating the determinant. But what if the determinant is non-zero, what is the inverse? So here's one way of finding an inverse. For the 2 by 2 case, it's easy enough that you can just memorize this formula. That originally we had a matrix A of A11, A12, A21, A22. So these entries are switched over so that the inverse of A is now 1 over determinant of A times of these entries. For example, I will show you the example shortly. But for the 3 by 3 case, it's a little bit complicated. So when I take a 3 by 3 matrix, and if the determinant is not 0, then the inverse is 1 over determinant of B times these type of 3 by 3 matrix, where the entries are not the entries of B. Okay, so entries of B inverse in this matrix form is obtained by computing a special type of 2 by 2 matrix. So for example, if I want to compute C21, okay, then C21 is the determinant of 2 by 2 matrix obtained by deleting second row, because there's 2 in the first index, and first column. So after deleting second row, first column, I get these 4 entries, which consists 2 by 2 matrix. Because I just deleted 1 row and 1 column, still square matrix. So the determinant, so this bar represents the determinant of the matrices, is the value of C21. And also, the element of B inverse is not simplyCij's, because I have a negative signs here. Okay, so negative signs are alternating. So positive minus, positive minus, positive minus, positive minus, this way. So let me give an example here. I will give a simple example. So for example, let's say A is 1, 2, 0, 1. What's the determinant? 1, 1 times 1 times 1 minus 2 times 0, which is 1. So it's not 0. So we can find an inverse. So inverse is 1 over, so determinant 1 over 1 times what? See the formula here? You take the diagonal entries and switch over these 2 entries. So it's the same entry, so it's 1, 1 again. And also the second one is switched, but it contains a negative. So negative 0 and negative 2. So this is 1, 0 minus 2, 1. Now if you check whether this is actually an inverse, let's take the multiplication here, 1, 2, 0, 1, and 1, 0 minus 2, 1. So this guy is minus 1 times 1 minus 2 times 2, and this guy is 1 times 0 plus 2 times 1, and 0 times 1 minus 1 times 2, 0 times 0 plus 1 times 1. That's something weird, right? No, I think this formula is wrong here. So, sorry, so this is not the formula. So you don't invert this off diagonal. So minus 2, 0. So minus 2, so 2, 1. No, that's right. So if you take 1, 2, you have to invert this. So no, you don't invert this, right? So it's minus 2, 0. So A times 1 minus 2, 0, 1, right? That's the right one here. So sorry for that. Let me recompute. So here, 1 times 1 plus 2 times 0. 1 times minus 2 plus 2 times 1 here, and 0 times 1 plus 1 times 0, and then 0 times minus 2 plus 1 times 1. So you can do this in your head, but I just write it out so that you can review the process of application. So here's 1 and here's 1, and these guys are cancels to be 0, so we get 1, 0, 0, 1. Okay. Let me switch back to the slide. I think there's a typo in the slide. So, yeah. So this is 2, 1, and this is 1, 2. In that case, right, yeah. Now it makes sense. Sorry, so this is typo, severe typo here. How about 3 by 3? So let's talk about 3 by 3 here. Let's say 1, 2, minus 1, 0, 1, minus 1. Okay? And 0, 0, 0. So let's try to find whether this is singular or non-singular. What's the determinant? So in this direction, you have to take positive sign, and in this direction, you have to take the negative sign here, right? So on the positive side, I get 1 minus 1, 2, 1, 2 minus 1, and 0 minus 1, 0, and 0, 0, 1. And on the negative side, the blue one, I get minus, first one is 1, 2, 0, and 1, 0, minus 1, and the last one is 0, 0, minus 1. Okay, so all zeros disappear, so these are all 0, 0, 0, 0, 0. So what level is minus 2? And the determinant is non-zero, means that there is a inverse of b. So let's find out the inverse. So we have b inverse, and this is 1 over negative 2, the 1 over negative 2 of what? C11, C21 minus C31, and so on, and minus C, here we have 1, 2, C13 and C22 minus C23 minus C32 and C33. Let's try to find out C11. So I think this computation is long, so keep that in mind, that this already is a long computation. So what's C11? So I have to delete the first row in first column and then take the determinant. So this is the determinant of 2 minus 1, 0 minus 1. But this is minus 2. Okay. And what's C21? So I have to delete the second row first column. Okay, second row first column. I get 0, 1, 0, minus 1. That's 0, right? And what's C31? That's the determinant of what? Third row and first column. So I get 0, 1, 2, minus 1. minus 2. Okay, so I got first row. It freezed, so make it normal. Okay. So, and let's see here. Let's try to get this part. So what's C12? So that's the determinant of deleting first row, second column, right? So this is 0, minus 1, and 0, minus 1, and that's also 0, right? And what's C13? That's a determinant of deleting first row and third column, 0, 2, 0, 0. So that's 0, and so on. So if I take the sum of the few entries in the B inverse, then it's 1 over minus 2 of C1 is minus 2. Here I have 0, minus 2, and here we have 0, 0. Okay. So, and let's say, I don't know yet, this, you have to compute these parts too. So what's B times B inverse? So you have to multiply this 1 over negative 2 on every 9 entries. So this is basically 1, 0, 1, 0, 0, and star, star. Okay, so these stars are not the same stars. I just take the negative 1, divide by negative 2 on these stars. So these are some different stars. Okay. So when I compute this, what should I get is 2 minus 1, 0, 0, minus 1, and 1, 0, 1, 0, 0, and something here. I should get 1, 1, 1 on the diagonal, and all the off diagonal has to be 0. Let's see. Well, if I take the first row and first column here, I get 1, right? And I have to do the other ones. Well, let's say, let's try to find out what this part is. So what's the C23? So C23 is determinant of deleting second row, third column. So this is 1, 0, 0, 0. So that's 0. So here we have 0. 0 already. Yeah? So I want to find out what's the third row, second column entry of B times B inverse. So third row, second column. But whichever the element here is, because I'm multiplying with 0, that's going to be 0. And also I'm multiplying the negative 1 to 0, so this is going to be 0. This is 0. Third row, second column. So there are 9 entries here. I didn't put every entry here. So if you've done all the calculation, you will see that all the entries are 0, and except for the diagonals. So diagonals are 1, and all the others are going to be 0. Okay. In fact, you don't have to compute this by hand. For instructive reason, you can do your computation by hand once, but I will show you how to use the MATLAB to find out the determinant of matrix. Okay. All right, let's move on. So, where this matrix used? So it's used when we solve the system of equations. So suppose that we have n unknown values, which is denoted by x1, x2, and xn. And we have a system of equations to solve n number of equations to solve these unknown values. So I can express this system as a set of n equations, but using matrix, you can make it into one equation as follows. In this form. Okay. So why is this one equation? Because you can denote your matrix, this n by n matrix, m by n matrix as A, and you can denote this column matrix as X, and then this constant column matrix as B. So usually the matrix, if the matrix is row matrix or column matrix, you can identify that as the vector. So usually we denote it X vector, B vector here. Okay. So this equation is simply one equation. Okay. It's a very simple equation now. So how can you relate this system of equations and this expression? You see, the first line of this system is saying that this linear sum is equals to B1. Now, if you're looking at this matrix equation, if you equate these matrix and this matrix, then what I mean by these two matrices are equal is that these two matrices are equal entry-wise. So the first entry of the matrix on the left is A11 times x1 plus A12 times x2 until A1n times xn. And that entry, which is the first entry of the left matrix, is equals to the first entry of the second matrix, which is B1. So that's the first equation in the system. And the same for the next other equations. So in the linear algebra, we talk about the linear operation to reduce the matrix A into simpler form, which allows us to find the solution in easy algorithm. But we're not going to talk about that here. It's not important. So let me skip this one. So it's just jargon, just the jargon. And also this part. Well, let me explain this part and then move on to the differential equation part. So usually we're not going to talk about the matrix in the full form. When I take the matrix A in this way, you have to understand what that means. So first of all, let's say A times X equals to B means that this X is a column vector, which is column matrix Xn, and B is B1 to Bm. Okay. So usually this n and m, the length of two vectors, doesn't have to be the same. But if you want to find a unique solution, you need to have a same number of equation as a same number of variable, right? So we're not going to talk about the general case when we have two different indices. So we're going to only talk about when you have the same number of equation with the same number of variable. So by the definition here, we have vector x is n by 1 matrix, right? And B is also n by 1 matrix. So you can assume that when I take this equation, then this matrix A must be n by n matrix, because that's the only when you get the matrix B of size n by 1 by canceling out these two, right? So A is n by n matrix. And now I can express my columns of matrix A as a column. So let's say A1, A2, AN, which means that this is n by n matrix. Okay, it seems like it's 1 by n matrix, but I'm taking this A1 vector and until AN vector, where AI vector for I from 1 to n is a column matrix. So which is this 1i, A2i until ANI. Okay. So if I use these notations, it seems like I'm taking the matrix inside of matrix, right? So A11, so this A1 vector is A11, A21, and AN1, and here is 1, 2, A22, AN2, and so on until I get A1N, ANN. So usually we don't do this. There's no matrix inside the matrix. Well, you can, but what I mean by this matrix inside the matrix is I'm not going to talk about this matrix's signs here. So I'm just considering this as a one big matrix, dropping all the matrix parentheses inside of the matrix. So just take it as original n by n matrix. Okay, A11 to ANN. So this is by convention. Traditionally, we just do this. Okay, but what's the offset of writing this matrix A as the some type of the row matrices of the vectors? So then expression gets really simple. So this expression can now be written as A1 vector to AN vector times x1 to xn equals to B1 Bn. Right? Or you can just write it as B vec, this as a V vec. Now you can take this matrix as if it's 1 by n matrix. So this is 1 by n matrix, and this is n by 1 matrix. So you can take a multiplication here. So what happens is you get 1 by 1 matrix, which is just the entry 1 matrix with 1 entry, which is just same as the value, right? So x1 A1 until xn AN. And that's equal to what? B. So this expression, A times x equals to B, it can be written in the same way as this expression, where each AI is taken as a column vectors of the matrix. And what's the offset? Well, this is the matrix expression, and this is the vector expression. And this is matrix expression. They are telling the same thing. They are telling the system of equations. But when you represent in the vector expression, it's better to understand the nature of this system, because what you're going to find is the value of x1 and xn, but what you really want to find is whether your vector v can be written as a linear combination of a1 to an. So there are some vectors you cannot represent with we cannot represent with the vectors. For example, in three-dimensional space, if this is x, y, and z axis, suppose that you have two vectors in xy plane. So this is a1 and a2. And suppose that you take the vectors whose z coordinates are not 0. For example, let's say I take this as b. Okay? B cannot represent as a linear combination of a1 and a2. If you take the coefficient, any coefficient on a1 or a2 and multiply them together, you always get a vector inside of a xy plane. You're not getting a vector with non-zero z coordinates. So finding the solution is checking whether this given b, given constant vector, it can be represented as this linear sum, where this linear sum contains the vector which comes from the matrix, and matrix A is come from the system, and the system, so therefore you're checking whether system is solvable or not by finding x1 and xn. Okay, so that's deep nature of this matrix multiplication, and that will be also covered in the linear algebra if you take that course in next year. So let's move on. Now, eigenvalues and eigenvectors. So we are doing this only because we need this for solving differential equations. So we are going to solve that in the next lecture. For now, we just review the definitions. So let A be a square matrix. It has to be square matrix. And consider an equation that A times X. Now, X is not a number. This is the vector. So which means that this is the column vector. When I take the column vectors in the matrix multiplication, it's always represent the column vector, okay? And suppose that this A times X is equals to some constant lambda times X. Then this lambda is called eigenvalue, and X satisfying this equation is called eigenvector associated to this eigenvalue lambda. So how do we find such lambda? If you find lambda, then it's easy to find X. You have to first find the lambda. Lambda can be found by solving the characteristic polynomial. The characteristic polynomial is defined by the determinant of A minus lambda times identity matrix equals to 0. So remember that when you take the determinant, it's just the multiplications of entries and sums over these multiplications, right? So it's just a polynomial expression. And since we have an unknown variable lambda, this is going to be the polynomial in terms of lambda, okay? Let me give an example. Let's try to find eigenvalues and eigenvector of this matrix, 2 by 2 matrix. If the size of matrix gets larger, it's hard to find eigenvalues and eigenvector. If you're using only your hands, then I think 3 by 3 matrix is in general, the largest matrix that you can find the eigenvalue or eigenvectors. For larger sizes, just use the MATLAB or other tool. Don't use hand. So we have A equals to minus 4. And this is also 4. Yeah, 4 minus 1.2, 1.6, and 1.2. Okay. Let's take A minus lambda I. So minus 4 minus 1.6, 1.2 minus lambda times 1001. So when I take the lambda I, the I must be the same size of the size of A. A is always square matrix. So if A is 2 times 2 matrix, then identity matrix is also 2 times 2 by 2 matrix. So this is minus 4, 4, minus 1.6, 1.2, minus, now I have to multiply lambda everywhere. So lambda 0, 0, lambda. So when I take the subtractions, I have to take the subtraction on entry-wise. So we have minus 4 minus lambda, okay? 4 minus 0, minus 1.6 minus 0, 1.2 minus lambda. And then take the determinant of this matrix, okay? What's this? So minus 4 minus lambda times 1.2 minus lambda minus these off diagonals, 4 times minus 1.6. So here's the lambda square, and here's minus 1.2 lambda plus 4 lambda minus 4.8 and plus 6.4, right? So this is lambda square plus 2.8 lambda plus 1.6. So I hope my calculation is right because this is recorded lecture. If it's wrong, no one can help me. So, okay, so let me take this in fraction form. So we have 14 lambda plus 8 over 5. So this is, so if this is 0, then I'm solving 5 lambda square plus 14 lambda plus 8 equals to 0, right? So this is lambda minus 7 plus minus 49 minus 40. Okay, it seems like it's correct because the answer seems nice. So minus 7 plus minus 3 over 5. So it's negative 2 or plus 4 is negative 4 over 5. Okay, so lambda is negative 2 or negative 0.8. So when you're finding an eigenvalue, you don't have to worry about whether your calculation is correct or not, because it will be you will know whether your lambda is correct or not when you find the eigenvectors of each eigenvalue. So lambda, let's suppose that I want to find the eigenvector of associated to the eigenvalue lambda minus 2. Okay. Then let's say V1 be the eigenvector of eigenvalue minus 2. So then, by definition, A minus of minus 2i times V1. So this is the vector, so it's a 2 by 1 matrix, column matrix, okay, equals to negative 2 times V1. So I want to find, so V1, suppose that this is A1, A2. I want to find that minus 4 plus 4 here on the first entry, and 4 and minus 1.6. minus 4 plus 2, 4 minus 1.6, and 1.2 plus 2 times A1, A2 equals to 0, 0. So I get minus 2A1 plus 4A2 equals to 0, minus 1.6A1 plus 3.2A2 equals to 0. So these are basically the same equations. All we know is that A1 is equals to 2A2. So I cannot find a unique V1, but there is a one particular V1. If I plug in A2 as 1, then if I take V1 as 2, 1 matrix, then this always hold. Okay, so I'm not saying that there's a unique eigenvector. I only need one eigenvector. Okay, so this is eigenvector of eigenvalue minus 2, and you can find another eigenvector for eigenvalue minus 1.8. Okay. And this technique also will be used later, important in the solution of the system of differential equations. Okay. So your system of differential equation now can be written as a matrix. So suppose that you have y1 to yn functions. Then suppose that you have n first order differential equations and written as follow. Okay. So this can be written as the following. If you take the y1 to yn as an entries of the column matrices represented by vector y, then by taking vector y prime, you're taking the derivative of each entries. So y1 prime to yn prime. Okay. And on the right hand side is simple matrix multiplication, because this a11 times ay1, a1n, yn, now given by a times y, right? So your system of differential equation can also be written as a matrix multiplication, right? So here's the theorem. So we will give it the example later. So theorem says, suppose that you have a system of differential equation y prime equals to ay, okay? And suppose that this lambda is the eigenvalue of a, and v vector is corresponding eigenvector to this lambda. Then this expression is a solution to our equation, this equation. Okay, what does it mean by this equation? It seems weird. Let me show by example. Suppose, and then further, if you have n distinct, it's very important, distinct. And it means that none of these values are the same. And it says n distinct eigenvalue. So we have n number of equations, and we have n distinct eigenvalues with eigenvectors. Then this is the general solutions. So let me show you with the example here. Okay. To do that, let's find out the other eigenvalue here. Other eigenvector for eigenvalue minus 0.8. So a minus 0.8 times I times v equals to 0 gives minus 4 plus 0.8, 4 minus 1.6, 1.2 plus 0.8 times, let's say this is v2, and let's say b1, b2 here. That should be 0. And this is minus 3.24 minus 1.6 and 2 times B1, B2 equals to 0, 0. So I have minus 3.2 B1 plus 4 times B2 equals to 0 and 1.6 B1 plus 2 times B2. Now, well, these are the same equations. So we have simple one is B2 is equals to 0.8 B1, right? If I take this one. So I can take V2 as, if I simply put B1 equals to 1, now this is 0.8. Okay? Or you can take the other ones. Suppose that I take B1 as 5, then this is also work as eigenvector. Okay? So summarize. We had 2 eigenvalues and 2 eigenvectors. So if lambda is minus 2, my eigenvector can be taken as 2, 1. And if my lambda is minus 1.8, 0.8, then my eigenvector is, I think this is better, right? So 5, 4. Now, let's think about this system of linear equations. Suppose that my x and y are both function of t, and it satisfies x prime t is minus 4x t plus 4yt, and y prime satisfy minus 0.6 xt plus 1.2 yt. It's freezed again, so okay. So then, if I take y vector as simply x and y, right? So this is a function. It's a function of t, and the value of function is a vector. It's a perfectly normal function. Then this y vector prime is now written as a times y vector. So this is our differential equation represented in terms of matrix expression. Okay? So now what does this theorem says? It says if you know the eigenvalues, and the eigenvalues are all distinct, and since this is a there is a two sets of two equations, and we have two distinct eigenvalues, then the general solution is y equals to c1 e to the negative 2t times v1, okay, plus c2 times e to the negative 0.8t times v2. I forgot putting t here. So so let me make a correction here. So here is a t, okay, lambda 1, lambda, and t, okay. So let me write further here. So what that means is that this is a constant number, okay. It's a variable, but it's just a constant if I plug in t. So this is c1 e to the negative 2t of 2, 1, and c2 e to the negative 0.8t of 5, 4. Okay. So if you make it into one single column matrix, then this is 2c1 e to the negative 2t plus 5c2 e to the 0.8t, and then c1 e to the negative 2t plus 4 times c2 e to the negative 0.8t. Okay. And what was the y vector? It consists of two functions, xt and yt. So this expression solves the general solutions of xt and yt. So it simply says that the solution of this differential system of differential equation is xt is equals to 2 times c1 e to the minus 2t plus 5c2 e to the negative 0.8t, and yt is c1 e to the negative 2t plus 4c2 e to the negative 0.8t. That's just the general solution, okay? And you might wonder, when we solve the single differential equation, if you have a constant multiple on this arbitrary constant, we can make it into one, you can drop this constant, right? But you cannot do this here. We cannot change 2c into c1 or 5c2 into c2 because it says, this expression says, if I determine c1 here, then if I determine the coefficient of e to the negative 2t functions in the function of y, then the coefficient of e to the 2t's function in the solution x is twice of that coefficient. They are related. They are not independent variables. They are not independent constants. Okay, so they are related. So these constants 2, 5, 1, 4 is very important. You cannot just get rid of these constants because these constants are related. And why is it related in the first place? Because these functions are related by the two equations, two differential equations. You cannot solve this solution. You cannot find a solution by singling out this one differential equation. You need both differential equations to find a solution. So if you determine one equation, if you determine one solution, the other is also defined, right? So they are not independent. So x changed, then y also change. So that's why these coefficients are related. Okay, I think that's it for today. And I have something to show you on the MATLAB, but I think time is past too much. So I will stop here. And this was the recorded lecture. So if you have any questions, please send me an email, and we will do the rest of the slide next time. So thank you for listening, and have a nice lunch.